This is part 2 of a presentation Wyken Seagrave gave to the Derby Scientific Club on the 10th of February, 2009, with the title History of the Universe, Fact or Fiction. In part 1 he had explained the creation of the universe and the working of stars.
As these heavy atoms came out of the exploding stars, they stuck together. They stuck together typically through a process of forming ices, and so you get dust grains with icy mantles on them. This is a photograph of one that was collected and brought back to Earth. And the icy mantles are quite important. Obviously it's very cold out in space. You're now far away from the star, so you've got to imagine a cloud of gas and dust. These icy mantles tend to stick together, and here are the 4 atoms. The icy mantles, when the next generation of stars is formed, those icy dust grains tend to stick together and form disks, planetary disks. And they stick initially because of the ices, and then as they get bigger, gravity then tends to take over, and they tend to clump together to form planets. So you get a star in the middle, but now with a disk around it, and that disk gradually forms into icy snowballs and then into planets. And that's why the planets today around the sun are formed in a disk. And not a lot of people know that. I've seen children making models of the solar system with the planets all scattered all around, and remember this girl's father had helped her to make this. And neither the father nor the girl had any idea that the planets are arranged in the form of a disk. And they're arranged in the form of a disk because of the way they were formed. So, and that's why we get this ecliptic, where the planets move through the night sky. So we get possibly around 8,000 million years ago, we get the early planets. And those early stars will then explode in the same way. And we're not sure. It could be that there were many generations of planets. Early planets, they were destroyed as their stars exploded. Now, when you think about the origin of life, we've got something like life, we think, started down here when the Earth started. We've got all this time when early chemistry could have been happening on planetary environments or out in space. And we've only just begun to think about what kind of chemistry could happen then. So we're in the infancy of trying to understand how life began. Anyway, those early planets will have been destroyed as their parents became supernova, and eventually the solar system was formed in exactly the same way as these other planets. And we know that there are many planetary systems. We've detected hundreds of planetary systems nearer the stars. It's very difficult to see them because they're very dim. Planets obviously don't shine, and they're near to bright stars, but we can detect them by the wobble that they cause in their parent stars. So we've detected other planetary systems, and we've no reason to think that the Earth and that our sun is any different from any other star. So we might suspect that there could be billions of planetary systems out there. We don't know, but we've detected hundreds near us, and I suspect that there might well be thousands or millions or billions of planetary systems, any of which could contain life in some form or other. The origin of life could well have been rooted in the history, in those early generations, or it might be such an exceptional thing that it just happened to happen on the Earth. We don't know. We've got no idea really how unusual life is. It could be that the history of the Earth has somehow been instrumental in starting life off. What happened was that as the Earth cooled, all the heavy atoms, typically iron, fell to the centre of the planet, heated it up and it melted. The gases, which were originally the icy molecules on the dust grains, they will have boiled off, and we'll have got an early atmosphere. So around the planet we'd have got a thick atmosphere, the process called degassing, and these are the gases that we would expect, methane, ammonia and water, would have occurred in the atmosphere. Important to notice that there would have been no free oxygen. We're very used to a planet with oxygen on. Oxygen is very special, very unusual. The oxygen, as far as we know, free oxygen such as we have on our planet, can only be made by life. And in fact, that's the characteristic signature that they search for when they're searching for life, is to say, has it got free oxygen? Because it's not natural. The natural process is for atoms to be combined with hydrogen. And that you might know, if you combine oxygen with hydrogen, you get water. Because there's so much hydrogen. Remember, the universe started with hydrogen and helium. Helium doesn't do much, it's inert. But hydrogen combines very readily with most things. So most things in the universe are combined with hydrogen. When you see oxygen that's not combined with hydrogen, that is special. And that can only, as far as you know, only be created by life. Originally there would have been no free oxygen, so we couldn't have survived in those days. Somehow life began. Here's a quick diagram of how life works. So you've got genetic material. There's a complicated piece of machinery focusing on a complex of molecules called the ribosome. The ribosome is central to the way life works. And the ribosome takes the instructions that are encoded in these genes, and it uses them to build proteins. So the flow of information is from DNA, which is these genes, through this other form of information called RNA, into this ribosome. The ribosome is actually a combination of genes and proteins. It's a strange and extraordinary piece of machinery, and it works to build up a long chain of amino acids. And the amino acids, once they're put into water, they fold themselves up. So there are 16 or so common amino acids, and the order that you glue them together depends on the information in these genes. That is how life works, or a major part of it anyway. A lot more to say about it, obviously. How could that possibly have, that system possibly have formed, is one of the key unknowns about the story. There are lots of different theories and lots of facts to bear in mind. Organic molecules, these ones that we've talked about, are very common. The origin of life is a mystery, as I've said. Could there have been an earlier molecular system which didn't use the same molecules that we know? Could it have evolved? Some people think that life started by adsorption onto clays, and that somehow it then evolved and changed to the present system. And could it have been formed somehow by geological process? Instead of forming in the air, could it have formed at the hot spots under the oceans? Or indeed, could it have formed somewhere else and come to the Earth by drifting in meteorites being brought here? We've got no idea, basically. So that's one of the exciting areas which our children will continue to work on. One of the key themes of the story is interdependence. All these different factors work together. For example, we've already talked about how geology could have affected life. Okay, quick zip through then. We're now covering most of Earth's history from when life started about 4 billion years ago to when we get these early animals, such as we would recognise. That period covers most of the history of the Earth. And throughout a lot of that period, Earth was in the form of bacteria. So we have bacteria about 3.5 billion years ago. And about 2 billion years ago, we get a completely new form of life, which is where a bacterium is like a factory. If you think of a model of a city, or a plan of a city, and you have a factory, like Rolls-Royce would represent a bacterium. The whole city would represent this larger form of life, having several different factories working together, and also having a library. In the bacterium, there's no library for all the information, for all the DNA, the genetic information is just scattered around. In the city-type organisation of the eukaryotes, we have a library where all the information is brought together in the nucleus. So with the eukaryotes 2 billion years ago, we get the nucleus. And we think that what happened was that bacteria lived together. And there are different parts of a eukaryotic cell. The mitochondria are absolutely the classic example. The bits of our cells, our bodies are made of these eukaryotic cells. And bits of our bodies that take molecules and turn them into energy, allow us, or take fat, for example, and turn them into chemical energy that can be used to do work. Again, this is a fascinating story about how this thing works. But those cells, the mitochondria, are about the size of a bacterium. We get this 4 billion years where life developed up to the level that we would call invertebrates. And invertebrates occurred about 500 million years ago. So we've now come to about within the last 5% of the history of the universe, and we've got to the age of invertebrates. This is where now most people know. Oh, whoa. Slow down. Most people have got some idea what happened then. We get the vertebrates appearing, typically fish. The fish came out of the water, so we get amphibians and then reptiles. And we get dinosaurs. We get the extinction of the dinosaurs. And most people, I think, know this general theme of the story. They perhaps don't know the other things that were happening, as well as the vertebrates evolving, the invertebrates and the plants were also evolving. And in fact, there are very close similarities in the evolution of these three groups: the plants, the invertebrates and the vertebrates. And the evolutionary theme that you see in each is that, first of all, you depend upon water for your reproduction. So in plants, for example, it would be the ferns. They have to have water, or not lichens, ferns. Ferns reproduce by their sperm swimming freely in water. Fish have to reproduce in water. And invertebrates also, the early ones, had to reproduce in water. And then there was a phase of getting free from water. So the amphibians learned to come out of the water, but they were still tied to the water for reproduction. Same thing with the plants. They still needed water for reproduction, but they grew out of the water and could grow along land, except during their reproductive phase. And the invertebrates are the same. And then these three groups evolved ways of reproducing without water, so internal fertilization. And you see exactly the same thing in all three groups. So that's another one of the lessons that comes out of taking this broad view. You can see these trends. We are living through a time now of dramatic changes in reproductive technology. We've already got man-assisted reproductive techniques for humans. Okay, so in vitro fertilization, is very common. If you look at these trends, I would predict that that kind of technological change will continue, and we will probably end up, because the whole reproductive cycle is a huge limitation on human development. You have to get the head through the birth canal. That limits the size of the baby's head. If we could get away from that, who knows what kind of evolution we might have. If you look at trends in evolution, that might be one of the things that the trends might tell you. Anyway, dinosaurs about 65 million years ago. So we've left the billions behind now. We're down into the millions. Apes, about 3 million, and people, it says here, about 25,000. Very, very recent. During the last ice age. Depends how you define people, and you might argue about that figure. That's the story.
That was part 2 of a presentation Wyken Seagrave gave to the Derby Scientific Club on the 10th of February, 2009, with the title History of the Universe, Fact or Fiction. For more information on this topic, visit www.historyoftheuniverse.com. In the third part, he explains how he tells this story as a work of fiction. For all 3 parts, visit www.timecrystal.co.uk.